recap of last lecture on the subthreshold current. So this is the current when the gate voltage is smaller than the threshold. So we still have small currents. So if you want to see this current, then you have to draw the log scale of the current versus the gate voltage. And if you do this log scale of the current, then you will see this subthreshold current here like a straight line. Because this is in log scale, that means it's exponential. So here we give some derivation of this subthreshold current. Essentially, the subthreshold current is due to the diffusion current of the electrons over this barrier top. And then, because of the number of electrons that have higher, let's say the energy higher than the top barrier, so the number of electrons decays exponentially when you increase the energy level. This is due to the Fermi function. So then here, when you change the barrier top because of the gate voltage, because gate voltage is going to push down this barrier top. So the barrier height change due to the gate voltage. And then the number of electrons that can be over of the barrier also exponentially change with the gate voltage. That's why the current exponentially depends on the voltage, gate voltage. So we would say the subthreshold current is dominated by the diffusion current, while the unsteady current, for example here when you have the saturation region, this is unsteady current, then the current is dominated by this drift current. Because once the electron move over this barrier, it will fall down. So this is the drift. And if we do the derivation, then eventually we can get this equation for the drain current below the threshold voltage as a function of the gate voltage. And then it's strictly dependent on the drain voltage here, but typically this is very small when the VD is large. So you can ignore this term, so eventually you only have this one. So this tells you the drain current exponentially depends on this gate voltage. So if you draw this will be a straight line in this log scale plot. So any questions here? And then if you consider the subthreshold current, this is very small, almost zero. But if you consider that, then this is the equation. And then we define the unsteady current as here. That is the maximum current you can get out from the transistor. So this happens when the gate voltage equals to the drain voltage equals to the power supply voltage VDD. Offset current is here. This is when the gate voltage is zero, but the drain voltage is still VDD. So you have this small current, and this is the off current. So we care about this off current because we said that this is the reason that even your phone is in the standby sleep mode, then it's still consuming the power. Because the off current is coming from the power supply, right? Then this I off times VDD is the leakage power per transistor from the power supply. And you think about there are so many transistors on the chip, as we discussed at the very beginning of the semester. There are like 1 billion transistors on your processor. So you can imagine the power. Although each is small, but you have like billions of transistors on chip, then you will have a lot of leakage. So this is the impact of the off-state current on the leakage power. And if we want to further understand the subthreshold slope. Here, this is the definition of the S factor. And this is defined when the current reduced by 1 decade, 10 times. So the voltage you need to reduce. And here we say that this S factor is always equal or larger than 60 millivolts per decade. This is due to the physics here. The physical constants, like the thermal voltage, and the natural log 10 is when you convert the unit from the base 10 to the, let's say, base E to the base 10. So of course this depends on the temperature. This 60 millivolts per decade is for the room temperature. If you operate your transistor at lower temperature, then of course the S will be smaller. So if you want to understand the transistor better, then this band diagram is very helpful. So ideally, the transistor should be gate-controlled device. So when you apply the gate voltage, then you are going to change the barrier top towards the source side. However, when you apply the drain voltage, ideally, this barrier will not change as the drain voltage. Then the IDVG curve will look like this. We have given the drain voltage, still the off-state subthreshold current is similar. So this is the ideal case. But in reality, when you change the drain voltage here, then this barrier top will also be reduced. That means the current will be larger because more electrons can jump over. So that means the off-state current will increase here when you change the drain voltage from 0.05 to 1 volt. Then because the barrier top reduced by the drain voltage, so the subthreshold current also increase. So this is this Biebel effect, drain-induced barrier lowering. So this is the device that most of the gate control. So any questions? All right, so that's the review of the last lecture. And today we are going to continue